The British Museum occupies a 13-acre quadrangle inside the Bloomsbury Street grid, built in disconnected stages over 200 years. Because the architecture was added piecemeal, the layout lacks a single chronological logic, making the site difficult to navigate as a historical timeline. Viewed through the lens of engineering, however, these 13 acres function as a single, massive physics problem. Every wall, column, and roof on the site serves the same mechanical purpose, directing millions of pounds of gravitational weight safely into the Earth. The solution to that problem begins at the front door. This is the ground line, a boundary running 113 meters along the south front. This is the interface where the stone structure ends and the soil begins. To understand how the museum stays standing, we have to follow the weight. We will start at the very center of the site, at the highest and lightest roof, and track the load as it travels outward and downward toward the foundation. By tracking the gravity instead of the history, we can see the hidden structural logic that dictates how these buildings were actually shaped. Look at the gap bridged by the Great Court Roof, finished in 2000. It is the highest point on the site, spanning the space between a rectangular courtyard and an off-center circular room. Because that circle is pushed toward the north, the distance between the two structures changes at every point. Spanning this irregular gap required a roof that holds itself up through geometry rather than heavy mass. The 800-ton steel grid shifts and settles into a specific mathematical curve that distributes forces across the entire surface. The shape does the work that thick, heavy stone used to do. The old walls underneath this roof have no internal cross-bracing. If the roof sags or expands and pushes outward at the edges, those 200-year-old stone walls will tip over. To protect the masonry, the roof sits on sliding bearings. When the steel expands in the heat or sags under snow, the bearing slides horizontally to absorb the movement. This ensures that the only force passing into the historic stone is a strict vertical downward load. The new structure resolves its own lateral forces, allowing the modern roof to coexist with the 19th century walls without compromising them. Step inside the central drum to see the 1857 reading room. From the floor, the 43-meter dome looks like a solid, heavy masonry structure, mirroring the stone domes of the ancient world. If you peel back the decoration, the masonry disappears. Underneath is a heavy, ribbed cast iron framework. This skeleton is doing the actual lifting, carrying the weight of the roof so the interior surface doesn't have to. The smooth dome visitors see is actually made of papier-mâché, pressed paperboard. It was chosen because it weighs almost nothing. It is a skin hung off a frame, separating the aesthetic surface from the structural work. This division allowed 19th century architects to achieve massive scale. By using a metal frame to carry the load and a featherweight material for the surface, they could build huge volumes without the crushing weight of solid stone. In the 1827 East Wing, the downward pressure increases significantly. This room was built to hold 65,000 books, creating a constant, dense load pressing down on the floor and its support beams. To span 15 meters without using columns, the ceiling relies on humped cast iron girders.
When a beam bends, the top edge is squeezed in compression, while the bottom edge is stretched in tension. These beams were cast with extra material at the center. Because cast iron is brittle and can crack when stretched, modern engineers strengthened the room by sliding welded steel tubes into the ceiling alongside the original iron. The new steel shares the load, preventing the old beams from reaching their breaking point. This provides reversible support. It adds the strength required for modern safety standards, while keeping the original 19th century engineering in place and undamaged. In the 1930s Duveen Gallery, we see how the museum actively manipulates weight to change the way art is displayed. Here, weathered fragments of the Parthenon are mounted at eye level along the walls. 2,000 years ago, these marbles were structural components of a Greek temple wall, helping to hold up a massive stone roof. In this gallery, the relationship is reversed. The marble holds nothing. Instead, the modern building supports the marble as an autonomous object. The modern 2014 edition uses a similar strategy to create open space. Architects pushed all the heavy mechanical gear and staircases into narrow servant shafts at the edges. By concentrating the weight in these dense cores, the main galleries can remain wide and structurally light. The heaviest function in the wing, dense collection storage, is pushed entirely below ground. This places the maximum weight at the lowest possible point, where the load can travel directly into a deep concrete slab in the soil. By treating weight as a variable, moving it to the edges or burying it deep, architects can keep human spaces light and open. At the south front, the journey of the weight reaches its destination. This is the oldest and heaviest face of the museum, where every downward force we've tracked must eventually resolve. This facade is built of pure mass. If you could see through the stone, you would find a core of brick and iron wrapped in a heavy coat of Portland stone. This density is designed to drive millions of pounds of force straight down through the columns. To manage the visual impact of this weight, the builders used entasis. They curved the middle of the columns outward very slightly. A perfectly straight column actually looks pinched to the human eye, so this subtle curve corrects the illusion, making the stone appear strong and upright. At the base of the columns, the weight enters a concrete raft over 2 meters thick. This slab spreads the concentrated force of the walls and columns across a wider area, allowing the earth to absorb the load safely. This brute mass is the simplest and oldest way to carry weight. It remains the physical endpoint for every ounce of steel, glass, and stone in the buildings above it. When you view these buildings together, the sprawling 13-acre site reassembles into a vertical stack of architectural evolution. At the top, lightweight geometry floats over the old courtyard. In the middle, metal frames carry weightless skins, and at the bottom, solid stone anchors everything to the earth. For 200 years, as technology and styles changed, every architect on this site was solving the same problem. They were all finding different ways to guide weight down to that same ground line. Every stone and steel member on this site serves this single purpose, guiding millions of pounds of gravity back to the safety of the soil.